Assalamualaikum. We will be presenting on gas chromatography. Gas chromatography or GC is an important analytical technique that is widely used in chemistry laboratories to separate, identify, and quantify volatile and semi-volatile organic compounds. For a compound to be analyzed using GC, it must be thermally stable and able to vaporize as the analysis is carried out in the gas phase. GC consists of key components including an injector, column with stationary phase, oven, detector, and an inert carrier gas as the mobile phase. In a gas chromatography system, the sample is first injected into the instrument and vaporized. An inert carrier gas such as helium or nitrogen acts as the mobile phase and carries the sample through a column that contains the stationary phase. The column is placed inside an oven which controls the temperature during the separation process, while a detector, commonly a flame ionization detector, is used to detect the separated compounds as they exit the column. Separation in GC occurs because different compounds interact differently with the stationary phase, based on their volatility and polarity. As a result, each compound travels through the column at a different speed and elutes at a specific retention time. This retention time can be used to identify the components present in a sample. Due to its high intense Due to its high sensitivity and efficiency, gas chromatography is widely applied in environmental monitoring, pharmaceutical quality control, and petrochemical analysis. There are two objectives for the experiment, which are to determine the retention time of 2-propanol and N-butanol and to identify the component present in a standard mixture based on its retention time.
Next is methodology. This is the block diagram of gas chromatography. Now I will explain the main components of gas chromatography. First is the carrier gas, which is used to transport the analyte through the column. The carrier gas ensures that the vaporized sample moves smoothly through the system for separation. Next is the sample injector. The function of the injector is to introduce the sample into the gas chromatograph efficiently. It promotes rapid vaporization of the injected sample and prevents sample condensation before it reaches the column. The third component is the column, which is where separation occurs. A PET column has a large diameter and lower resolution and is filled with coated solid support. A capillary column, also known as an open tubular column, has a narrow inner diameter with a thin stationary base on the inner wall, providing higher separation efficiency. After separation, the analytes pass to the detector, which converts the chemical signals into electrical signals. The film ionization detector is highly sensitive to hydrocarbons and is widely used. The thermal conductivity detector is universal and non-destructive. The electron capture detector is extremely sensitive to halogenated compounds and pesticides. Finally, the data system records the detector signals, plots chromatograms as signal versus time, calculates retention time and peak area, and performs quantitative calibration. This slide compares isothermal and temperature programming in gas chromatography. In terms of resolution, isothermal operation generally provides lower resolution compared to temperature programming. Temperature programming gives higher resolution due to optimized temperature gradients. For analysis time, isothermal methods usually require a longer time, especially for compounds with higher boiling points. In contrast, temperature programming can shorten analysis time because the temperature is gradually increased. Regarding peak shape, isothermal conditions tend to produce broader peaks for late eluting compounds, while temperature programming results in sharper and better defined peaks.
I want to explain the gas chromatography result for these two alcohol samples. So we have 2-propanol and N-butanol. Both samples were analyzed using a GC7890B instrument under an isothermal method at 17 degrees Celsius. So, our primary objective was to establish the characteristic retention times for these compounds to use as a baseline for future identification. So first, we have sample 1, which is 2-propanol. So, looking at the first report for 2-propanol, the chromatogram shows a very sharp, well-defined peak at 2.724 minutes. This relatively early elution time suggests that 2-propanol has a low affinity for the stationary phase under these conditions, likely due to its low boiling point. So, according to the area present report, the sample is exceptionally pure, with the main peak accounting for 99.98% of the total area. We see one trace impurity at 3.6 minutes, but it is negligible. So next, sample 2, which is N-butanol, and the primary peaks appears much later, with a retention time of 6.043 minutes. So the signification quite delayed over 3 minutes longer than the propanol is accepted, as N-butanol is a larger molecule with a higher boiling point, causing it to interact more strongly with the column's internal coating. So this sample also shows high purity at 99.85%, with 2 minor ghost peaks appearing before the 3-minute mark. So in summary, we have successfully characterized both standards, which is 2-propanol is 2.724 minutes and butanol is 6.043 minutes. In this series of experiments, we analyzed a standard mixture containing 2 primary components to observe how temperature adjustment influences peak separation and analysis time. We compared the result across 3 isothermal settings, which is at 17 degrees Celsius, 100 degrees Celsius, and 114 degrees Celsius. At 17 degrees Celsius, we see the greatest separation between the 2 peaks. At peak 1, it elapsed at 2.692 minutes, and peak 2, it elapsed at 5.903 minutes. While the separation is excellent, the second peak is noticeably broader and the total runtime is nearly 6 minutes. This temperature provides high resolution but takes the longest to complete. So next, increasing the temperature to 100 degrees Celsius significantly speeds up the process. So peak 1, it moves up to 2.269 minutes, and peak 2, it elapses much faster at 3.294 minutes. So when the temperature rises, the peaks become narrow and taller, which improves our detection limits. Finally, at 114 degrees Celsius, the analysis is highly compressed, which, as you can see, at peak 1, it elapses at 1.952 minutes, and peak 2, it follows closely at 2.225 minutes. At this high temperature, we save time, but we risk co-elution, where the peaks might begin to overlap, reducing our ability to distinguish between them. So, based on the area present reports, the mixture consistently contains roughly 37% of component 1 and 63% of component 2 across all 3 tests.
For discussion, GC is a technique for separating components based on their volatiles. The compound mixture are separated based on difference boiling point at the stationary phase. The separation is detected electronically by detector, and the electrical signal then processed via signal processor as chromatogram. The peak and retention time will appear in the result. Retention time is the time it takes for an individual component to elute from the column, while the peak represents one component in the sample. Retention time and peak resolution are affected by many factors, and one of it is the column temperature. When the column temperature increasing, the retention time will decrease. This can be thought of as reducing the analyte solubility. Conversely, lower temperature enhance interaction between analyte and the stationary phase, increasing retention time. When the column temperature is reduced, analytes interact more strongly with the stationary phase, causing them to elute more slowly and resulting in longer retention times. While this allows for faster analysis and sharper peaks, it often leads to reduced peak resolution because compounds may elute too closely together or overlap.
In this experiment show using gas chromatography to determine the retention time of 2-propanol and N-butanol. Each compound produced a clear peak showing that effective separation was achieved in the column. The compound in the standard mixture was identified by comparing their retention time with the non-standard. Compounds with lower boiling point pass through the column faster, while compound with a higher boiling point took a longer time to elute. It was observed that column temperature affected retention time. Higher temperature caused shorter retention times, while lower temperature resulted in longer retention times. In this experiment, show that GC is a reliable method for separating and identifying compounds based on retention time. Now I will explain about the example of tutorial question. For the example 3, in a GC analysis, name 2 common carrier gas. So it is hydrogen and helium. B, state one characteristic of carrier gas is chemically inert toward analyte. C, state the effect of injecting too much sample in the column. It can be column overloading, poor resolutions, and peak bordering. Explain why it may be necessary to do temperature programming to separate compounds with wide boiling point range efficiently. The next one is state one advantage of using a capillary column. It's a high resolution, high sensitivity, and short analysis time. For the question number 5, describe what is temperature programming in GC analysis. Explain why it may be necessary to run temperature program in GC. Temperature programming is used to accelerate the elution rate of the late peaks, otherwise take a very long time to evolute. Column temperature is increased either by continuously or its steps are the analysis process.